Namaste and welcome to this lecture on linear algebra through geometry. And in the last week we had looked at with the various systems of equations, like solutions to the system of equations, linear equations and stuff. And in this week we had looked at the idea of Gaussian elimination and Gauss-Jordan technique for getting the inverse. We looked at the idea of determinant of the matrix, and we also looked at the inverse of a matrix. At least we looked at the inverse of a 2 by 2 matrix, and for any higher order n by n matrix, computation of that inverse is a very cumbersome process. So what we are going to do is we saw that we could do this Gauss-Jordan technique in order to get the inverse of the matrix. This is basically going to the row reduced echelon form. We already said that given a matrix, it is always row equivalent to another matrix B. So that is something which we have seen. If the matrix is of course invertible, then it will all be equal to for a given matrix A. If the matrix is invertible, it will be row equivalent to the identity matrix. Now the question is like what is the purpose of the inverse? That is something which we saw in the last class, where we said that okay, in order to find the solution to the system of equations, say Ax equal to b, what you do is you do not really try to solve for Ax equal to b. If the matrix is a square matrix and it is invertible, we saw that given this let us say assume that we had a system where we said this is going to be A n by n, and we said okay, this is the input to the system, which is basically the n input variables you have, and you have b, which is let us say another n by the n output from the system. We said that if the matrix is invertible, instead of solving for Ax equal to b, what we did is you feed this b as an input to the inverse of the system. That means you feed b to A inverse and you get the output from A inverse, which was basically the solution that we had, that we looked for, x n by 1. That is exactly what we did, right. So the importance of inverse is that, like if you are given Ax equal to b and you want to solve let us say solve for x, what you do is if the matrix is invertible, feed this b as input to the inverse system and get back your system the solution that you are looking for. But as I said, this computation of inverse is going to be a very difficult process, a complex or a computationally intensive process. So what we want to do is and once you compute the inverse, then you solve for this. So that is going to be a bit difficult. So what we do is we see if there is any other way of solving this system of equations. Of course we just saw Gauss elimination technique, but there is something more interesting that comes out, which we will look at from the simple case of the system of equations, linear equations. Let us say we just look at 2 by 2 system of linear equations, and we will see something very interesting that comes out where the solution is given by the ratio of the determinants of something. Let us look at that and then try to come to a what do you call a general way to solve a system of equation where the matrix is invertible, right. So let us look at that. So suppose I have this matrix, let us say Ax is equal to b. Suppose we have Ax is equal to b. I am not going to take any a large matrix. Instead what I will do is I will just take a 2 by 2 system. So I am going to have this matrix A, which is given by let us say A11, A12, A21 and A22, and we know that x is basically the moment you write this system of equation, the matrix which is 2 by 2, naturally we know that there are only 2 unknowns, and the constants that we are going to have, again we just going to have 2 constants, say b1 and b2, right. This is what we have. Now let us do our high school way of solving this, where we try to eliminate one of these variables and then get that variable value, substitute that value into the first equation or the other equation and get the second variable. So that is how we used to do. So let us do the same thing here. So I have a11 x1 plus a12 x2 is equal to b1, and a21 x1 plus a22 x2 is equal to b2. Now what I am going to do is, let me call this as equation 1 and let me call this as equation 2. I am going to eliminate what I want to do is I want to eliminate this variable x1 So what do I do is I multiply the first equation, this is something which we know from our high school. We are going to multiply this with a21 and I am going to basically subtract. After multiplying I am going to subtract this second equation which I am going to multiply with a11. So I am going to do into a11. So let us see what do we get. I get a11 a21 x1 plus a12 a21 x2 is equal to a21 b1 and I am going to get a11 a21 x1 because I am going to multiply the second one with a11. So I am going to get a21 x1 plus a22 a11 x2 is equal to a11 into b2, right. Now we said that we will subtract this fellow from the other one. So what are we going to get? We are going to get this to get knocked off. So what we have is x2 into a12 a21 minus a22 a11 is equal to, I have a21 b1 minus a11 b2. Now which I am going to write this as, so x2 I can write this as a11 b2 minus a21 b1 divided by a11. I have changed the sign here, so I just wanted to swap the sign. So what I did is I took a negative from this and I took a negative from this, I rearranged the term. So I am going to get this a11 a22 minus a21 a12. Now if you substitute this value of x2 into the other equation, so what we will do is we will get the value of x1. x1 is also given by, so I am going to have this which is going to be a11 a22 minus a21 a12 and here what I am going to have is I am going to have b1 a22 minus b2 a12 is what we are going to have. Now what is interesting is if you look at the denominator of both x1 and x2, we see that the denominator of x1 and x2 corresponds to the determinant of A. If you look at this, we see that this is the determinant of A. So let us write that. So denominator for x1, denominator of let us call the expression for x1 and x2, expression for let us say x1 and x2, it is the same, it is equal to the determinant of the matrix A, right. So let us write that. So I am going to have x1 to be equal to b1 a22 minus b2 a12 divided by determinant of A, and similarly I am going to have x2 which is equal to a11 b2 minus a21 b1 divided by determinant of A. Now let us do something very interesting here. What is that? Look at the numerator in the first place now. Let us look at the numerator of x1 and x2, that means the numerator in the expression corresponding to x1 and x2, if you look at that also seems to be looking like a determinant of a 2 by 2 matrix, right. If you compare these two guys, if you compare the denominator and if you compare the numerator with this, we see that the denominator is the determinant of A, but then there is something that happens to the matrix A wherein which the numerator also looks like the determinant of some matrix where the column, the second column of the matrix A is retained, but then the first column of the matrix seems to be a bit different. Let us see what that is. So x1 is now given by, if I were to take this, let me take this, x1 is equal to b1 a22 minus b2 a12 by determinant of A. Now what do we have here? If you look at the numerator, as I said, it looks like a determinant. We know how this determinant works. So basically this is going to be the matrix which contains, in the first column let me take this as b1 b2 and the second column of the matrix is retained. So I am going to have a12 a22. So this looks like x1 looks like determinant of the matrix A with the first column of A replaced by the right hand side quantity that we had, which is basically the B1 and B2 values divided by determinant of A. Similarly, what we see is if you look at x2, the expression for x2 also is the same, but we see that the first column of A is retained. So, that means I am going to have x2 to be equal to determinant of this matrix, wherein the first column of the matrix is retained, A11 A21 is retained, and the second column seems to be replaced, the second column of A is replaced with the determinant, I mean with the right hand side column, the right hand side vector, that is B1 and B2 that we have. Oh, that seems pretty interesting. So, what have we done here? If you want to find the unknowns for a system of linear equations, suppose you have a system of linear equations with n unknowns, n linear equations with n unknowns. If you want to find the unknowns, all you need to do is simple stuff. Whichever variable that you want to find out, that corresponding column, if you actually see that it is always, if you look at this, let us say the first case where we looked at A11 x1, the system of equation is A11 x1 plus A12 x2 is equal to B1, and A21 x1 plus A22 x2 is equal to B2. We see something interesting here, and what is that? We see that the quantity or the unknown x1 always multiplies the first column of A, it does not multiply any other column of the matrix A, the coefficient matrix. So, we have A11 A21, A12 A22, and we have x1 x2, which is let us say B1 B2. Now, what is it that we see? The column of the matrix A, the first column of the matrix A is always multiplied by x1, and the second column of the matrix A is always multiplied by x2. Suppose if you take an A n by n matrix, you take an A n by n matrix. Now, what is it that we see? If you have Ax equal to B, this means I am going to have A n by n, you have n unknowns, namely x1 to xn, and that is going to give me B, which is B another n different values. Now, if you look at this A n by n, we still see that the first unknown x1 is going to multiply just the first column of A. The second unknown x2 is going to multiply the second column of A, third unknown by the third column of A, and so on. The nth unknown is going to multiply the nth column of A. Now, what did we see here in the previous case when you took the 2 by 2 matrix? We said that look, if you want to find out the value of x1, all you need to do is replace the first column of the matrix A with the right hand side vector or right hand side column matrix that you have. Find the determinant of that matrix divided by the original determinant of the matrix A, where you I mean the coefficient matrix that you had. Similarly, when you want to find out x2, this is pretty simple. When you want to do x2, what did we do? x2 always multiplied the second column of the matrix. So, what you do, replace the second column of the matrix with the right hand side column vector that you have and find out the determinant of the matrix, wherein which the second column is now populated with the right hand side column that we had, the constants that we had. Find the determinant divided by the determinant of A, and this is precisely what we call as Cramer's rule. So, Cramer's rule states that, so Cramer's rule to find out, and I mean this is not something which we did not know, but we were actually doing it, all these kind of the finding out x1 x2 and all those things, we know how to do it, but then what we see is we actually give a very formal structure now to it. We say that look, that is basically determinant by another determinant, it is basically ratio of some determinants. We will get back to one more insight in a bit now, but then let us look at this. So, what does Cramer's rule state? You have this A x n cross 1 is equal to B n cross 1, that means A is a square matrix. Assume that we already had in the previous lecture by Professor Krishna Kumar, where it said he said that look, the rank of the matrix is n. If the matrix A is a square matrix of rank n, that means the determinant, if the determinant is not equal to 0, then the matrix has a rank which is equal to the number of columns, that is basically equal to n. That is a finding that we had. Now, that is exactly what we are going to use. since we have brought in the idea of determinants here, that means the matrix A n by n must be a non-singular matrix, only then we will have determinant of A to be non-zero, is that right. So what we have is Cramer's rule states that for every xi, for I is equal to 1 to n, how do you find xi? Xi is nothing but determinant of the matrix A. I will put this as A1, the first column is A1, second column is A2, replace the ith column with B. This is basically my ith column of A, replace that with B and then go ahead with this. So determinant of this matrix divided by determinant of the original matrix A, where we had A1, A2 etc. AI etc. AN, right. This is the matrix that we had for I is equal to 1 to n, right. For I is equal to n 1 to n, you can actually find out the each of these what do you call the unknowns by taking the ratio of the determinants, right. Now again there is a small problem here. Getting the Cramer's rule to work for a higher dimension or higher size matrices is going to be again a computation intensive process, right. For 2 by 2 we can find out the determinant, it is very easy. Probably for 3 by 3 is also a bit easy, maybe 4 by 4 is easier, 5 by 5, 6 by 6 which starts becoming really computation intensive, because you need to find out cofactors and minors and a lot of other things which we actually, that is exactly why in that lecture on determinants by Professor Krishna Kumar he made it very clear, saying that look, as n increases computation of the determinant is quite tricky. So what you do is, okay, even inverse computation is very tricky, right. So what we do is we do not probably use Cramer's rule for large size matrices. There we resort to our idea of our what do you call the normal Gauss elimination technique or any other technique which we will see later, right. Now there is one more interesting stuff here. Now what is that? Recall that when Professor Krishna Kumar was doing this idea of determinants and stuff, he made one small statement where he said determinant of a 2 by 2 matrix, determinant of A 2 by 2 is basically the area of a parallelogram, whose sides are along the directions, direction of the column vectors of A, right. So that is what we said. So if you look at the Cramer's rule, what it says is it is going to be the ratio of determinant two determinants, right. If you take 2 by 2 like what we saw before, this is basically a ratio of one, the determinant which is basically area of one parallelogram, this is going to be area of another parallelogram, which we will see in detail like when we go ahead doing the vectors, when we look at the idea of vectors, which we will be seeing from the next week. So I will be looking at the 2 by 2 case and all those things, vectors in 2D and all those things from the next module onwards, next week onwards. There we will see in detail like what actually happens when you say when you are trying to do Cramer's rule, what is actually happening geometrically. That is something which we will get a lot of insight when we look into the idea of 2 dimensional vector spaces, which will be the topic of discussion for the next module. Now before we get into, let us look at one more insight. What is that? So let us consider this. Suppose we have this Ax is equal to 0. Suppose we have the homogeneous system of equations Ax equal to 0. Equations say Ax is equal to 0, and here again what I am going to do is I am not going to go beyond 2D, because if you understand two equations in two unknowns, I mean you can actually understand n equations in unknowns, I mean that is easy to get. So let us look at this now. So I have same thing, a11 x1 plus a12 x2 is equal to 0, a21 x1 plus a22 x2 is equal to 0. Now let us employ Cramer's rule to find the value of x1 and x2. So x1 is nothing but determinant of this matrix, which is basically the first column is 0, then you have a12 and a22 divided by determinant of this coefficient matrix, which is a11 a12 a21 a22. Now you see that in the numerator there is one column which is entirely 0, this will make the determinant to be 0, and this will make sense, the denominator will make sense only when the determinant of A is not equal to 0. So we will actually put this condition, determinant of A, let us say not equal to 0. When determinant of A is not equal to 0, what do we get? We get x1 is equal to 0, we also get x2 is equal to 0 when determinant of A is not equal to 0. And if you try to connect like what Professor Krishna Kumar told in the last class, you will see very clearly that if the matrix is invertible, then Ax equal to 0 has unique solution for a square matrix A, and that is precisely what we get here. So this is the only solution to Ax is equal to 0, right. I mean you can even do it the inverse way, where you see A inverse into 0 0, that will also tell you that the input has to be necessarily 0. So Cramer's rule is something interesting, where we look at ratio of areas, ratio of volumes and other things as we grow in higher dimensions, but the whole understanding is when we see geometrically what is the I mean you have let us say let us look at the 2 by 2 case itself. So what we have is we have a parallelogram here, we have another parallelogram that formed. So what is the change? That is exactly what we do, that we are going to look at, and in fact it also tells us something more. What is that? This determinant here is acting like a scaling factor, which is what we saw even in the case of finding inverse, where we said inverse is equal to adjoint of A divided by the determinant of A, and therefore the determinant of A acts like a scaling factor, 1 by det of A is the scaling factor. Therefore if for the Cramer's rule to work, what should be the condition? The condition is A should be a non-singular matrix. So let us write that. So to employ Cramer's rule, we will revisit, as I said, we will revisit the idea of Cramer's rule again when we do 2 by 2 and 3 by 3 in the later modules, where we will see visually like what is happening to the area and the volume, and what is the change that is being, that is what is the change that is happening if you replace those columns with the corresponding right hand side. Okay. So to employ Cramer's rule, the matrix A must be non-singular. Let us take a simple, let us take another example, let us do this. We had this equation 2x1 plus x2 is equal to 3, and we also had this equation, it says 2x1 plus x2 is equal to, let us say 4. Let us take this, right. Now let me see if I can apply Cramer's rule here to get the values of x1 and x2. So what is determinant of A in this case? Determinant of A is basically the determinant of this matrix, which is 2 2 1 1, and that is 0. Oh, that is a problem here. Why? Because if I want to find out x1, I will replace the first column with 3 4 determinant 3 4 1 1 by determinant of A, and that determinant of A is 0. Oh, that is a problem. So, we got into this divide by 0 problem, right. So, what is essential to note is Cramer's rule is employed only when the matrix is invertible. This will not work because you get into this divide by 0 thing. So, Cramer's rule, that is exactly what we have written here. We said the Cramer's rule, the matrix A must be non-singular, fine. Let us probably take our example of this 3 by 3 matrix, which in the last class Professor Krishna Kumar did, where we did elementary row operations and then got the values of x1, x2, x3. Let us see if that works here. So, I think the matrix was something like this. We had this matrix, what was that? Let us take this. We will take another 3 by 3 matrix. We say x1 plus x2 plus x3 is equal to 3. Let us say 2x1 plus x2 minus x3 is equal to 2. Then let us look at x1 minus x2 plus x3 is equal to 1. Yeah, let us take this matrix, let us see what happens. Now, first of all, let us find out the matrix A. The coefficient matrix A is basically 1 1 1 2 1 minus 1 and 1 minus 1 1. So, the determinant of A, we all know how to get this. Determinant of A is 1 into 1 minus of 1 into 1 minus 1 1. So, we are going to land in trouble. Let us see. So, this is basically 1 minus of this minus 1 minus 1. So, it becomes 0, then it is minus 1 into 2 plus 1 plus 1 into minus 2 minus 1. That is interesting. So, we have gotten into a problem where we have, let us see this. So, this is going to be 0 minus 3 plus, oh, we have not, thank God. So, this is going to be minus 2 minus 1 into plus 1, that is going to be minus 3. So, I am going to get minus 6, right. So, it is 1 into 1 minus 1 is 0, minus 1 into 2 plus 1, that is 3. So, minus 3, then plus 1 into the same thing, minus 2 minus 1, which is minus 3. So, you get minus 6, minus 3 plus minus 3, which is minus 6. Now, let us look at x1. What is x1? x1 is basically determinant of this matrix, where I replace the first column with 3 2 1, and the second column is all retained as that 1 1 minus 1 1 minus 1 1. So, you have 1 1 minus 1 1 minus 1 1. So, divided by determinant of A, which is minus 6. So, let us look at this. Determinant of the numerator matrix is going to be 3 into 1 minus 1 minus 1 into 2 plus 1 plus 1 into minus 2 minus 1 divided by minus 6. So, this gets knocked off, that is 0, and this is going to be, so we are going to get minus 3 by minus 6, which is plus 1, right. The matrix that we took was pretty simple. We will do the same thing. So, so the answer was like, I have chosen the matrix as that x1 is equal to 1, x2 is equal to 1 and x3 is equal to 1. So, let us look at x2 and see whether it works. So, this is going to be the determinant of 1 2 1 3 2 1 1 minus 1 1, yeah, 1 minus 1 1 divided by determinant of A, that is equal to minus 6. So, what is the determinant? I am going to get 1 into 2 plus 1 minus 3 into 2 plus 1 plus 1 into 2 minus 2 divided by minus 6. Did I make a mistake here? Minus 3 into 2 plus 1. So, this is going to be, let me just check the matrix once again. It is 1 to 1, yeah, 1 to 1, 1 minus 1. So, let us see, this is 3 to 1, 3 to 1, that is fine. So, minus 3 into 2 plus 1, okay. So, it is going to be 3 minus 9 plus 0 by minus 6, which is minus 6 by minus 6, which is 1. You do it, similarly you can get the value of x3. x3 can be obtained as, by Cramer's rule, and x3 value is one. Yeah. So, what is it that we see here? We see that Cramer's rule is used for solving system of equations with n variables and n unknowns, and the coefficient matrix that you have must be an invertible matrix, in the sense it must be a non-singular matrix. All those things should happen. Then you can take the unknown value to be the ratio of these two guys, right, the ratio of this determinant original, the determinant with the corresponding column replaced divided by the determinant of the matrix. Now, where are we going ahead from here? So, if you want to look at a whole, what we have done in the last two modules is basically we started looking at simple idea of system of linear equations. We looked at simple idea of system of linear equations. We try to figure out like how many solutions can exist for a simple set of linear equations or system of linear equations. We said that look, the system of equations can have either unique solution, that is only one solution, or infinitely many, or no solutions. There cannot be anything in between, that is what we saw. And we geometrically looked at like what does this mean. Like we said that in case of a 2 by 2 matrix, or in case of a system of linear equations in, let us say, two unknowns, I said that these are basically lines, and lines could intersect, lines could go parallel, lines could overlap. If they intersect at only one point, then you say that look, I have unique solution. If the lines are going to intersect at all the points, then you say you have infinitely many solution, and if the lines are parallel, you say that there is no solution. But we also had another case where the lines can pairs of lines can intersect at different points, and that is exactly where we got into the idea of no solutions and stuff. And we also looked at 3 dimension planes, intersecting planes, then parallel planes, and then you had the skewed planes and stuff, so where you do not have solutions. And having looked at all that, we also looked at special matrices, different types of matrices, matrix operations and stuff, which actually helped us to go ahead in finding the solutions to the system of equations. And towards the end, though we spoke about solution and a lot of other things, it was only in this module that we actually started looking at how to find the solution. So, yeah, we know that the solution is going to be unique, infinitely many, or there could be no solution. But if there is a solution, or if there are infinitely many solutions, the question was how do we find that, and that is exactly where we got into the the Gauss elimination technique and Gauss-Jordan form to get the Gauss-Jordan method to get the the solution to the system of equations. And in the process, we also looked at the determinant of a square matrix, and we had properties of the determinant. The reason why we had to look at determinant was when we studied the inverse, existence of inverse for square matrix is dependent on the determinant of the square matrix. If the determinant is 0, then the inverse does not exist. If the determinant is non-zero, then you can go ahead finding out the inverse of the matrix. And if you want to find out the solution to Ax equal to b, you will have the equation x is equal to, so the solution is given by x is equal to A inverse b. And we also looked at properties of inverses and stuff, And finally we said that okay, one more formal way of doing the finding the solution, which is basically the ratio of determinants, which is by the Cramer's rule. Now in both the modules what we have done is we have basically looked at the system of equations from the equations perspective, right. Now in the subsequent modules what we are going to do is, here we looked at in this module whatever we did, we looked at the row interpretation, or we looked at the equations and other things or the matrix from the row perspective. In the subsequent modules where we start with vectors from the next week, we will be looking at the matrix from the column picture or the column perspective. That means we just saw that the unknown x1 scales and the unknown x1 multiplies the column 1, unknown x2 multiplies the column 2 and so on, and that would corresponds to scalar multiplication of vectors and so on. So having got equipped with the idea of solving system of equations, invertibility of matrices, the most important concept, which is the rank of a matrix, because there are actually, if you look at a matrix, there are two numbers which are very essential. If it is a square matrix, the real number which is called the determinant is very essential, and of course the determinant not equal to 0 tells that the rank is n, and in other cases when the determinant is 0, the rank will give you very important information about the matrix, which we will see, like when you look at the idea of data science and machine learning, it has its own interpretation things. Now what we are going to do is, whatever that we have studied in these two modules right now in terms of solutions, determinant, rank, and a whole lot of stuff, transpose and all those things, we are going to have that in our mind for some time. In the next module onwards, we are getting into the idea of vectors and vector spaces and things, where we will revisit all these concepts and try to relate it from a vector perspective, and that will be the focus for the rest of the modules starting from the next module. We will look at vectors, vector spaces. Basically we start with 2 dimension, because here also we started with 2 equations and 2 unknowns. We are going to look at the same thing there, but here we are going to look at 2 component vectors in 2 dimensional plane. We are going to understand a lot of things, and we are going to look at a lot of other things like what you call transformation of vectors and things. We are going to look at that, interpret the system of equations from the vectors perspective, and we are going to get into a very what you call a wonderful journey into the space of vectors. So that will be the focus of the rest of the weeks, and towards the end we will look at some very interesting applications of linear algebra, which starts from probably our Fourier analysis that we do. It could be image compression and image reconstructions, and whatever that you do on your mobile phones. A lot of stuff, interesting applications are all there in the offering. So let us get into the journey of vectors from next week onwards. Namaste.